Hello and welcome to this tutorial video in which we're going to explore using Spec-ReX to explain vibrational spectra. So that could be Raman spectra or infrared spectra. We'll be looking at how to run some Python code using Google Colab, and we'll also look at some of the parameters that you need to keep an eye on when running Spec-ReX. But we'll begin by looking at a little motivation and background and why you might want to use an explainability method, in particular Spec-ReX. So let's get straight into some code. So this is just a Google Colab notebook. I've chosen this just so it's easy to access for everyone. This is just the free version of Google Colab. And also, for full disclosure, this little tutorial notebook, I did create it with GPT, I think version 5.5, I can't quite remember. But I've done that deliberately because I just imagine quite a few people might be interacting with Spec-ReX using an LLM. So I just wanted to go through this notebook and just to catch some of the little pitfalls that might result from using an LLM. And I've already just skimmed through this notebook quickly and already spotted a couple, so I'll point those out as they come along. This tutorial lives in a GitHub branch at the moment, so I'll be keeping that there for posterity, so everyone who watches this video can just follow along with this tutorial. Of course, if you don't use LLMs to code, then you should just better copy and paste what's needed from these various cells and run it on your own data. So I was quite surprised actually. The free version of Colab does let you run on a GPU, so that's great. We'll then download the data, and then we'll have a look at that and make sure it makes sense. The balanced data set, yes, GPT is a balanced data set. I'm not sure why it's chosen to focus on that. Maybe one thing to focus on here actually is normalized spectra. Actually, in this particular case, I happen to know that the spectra are already normalized, so that wasn't necessarily needed. But you need to know whether that's the case, because when you pass a spectrum into Spec-ReX, it assumes that you've done everything you need to have done to it for the model to understand. So, if you normalized in a particular way before you sent a spectrum into the model, then you would have to have done that beforehand, also before running a spectrum through Spec-ReX, because Spec-ReX will just take that spectrum and run it through the model. So just in this case, we've got 200 spectra. We'll just be taking a subset of those to demonstrate things. And let's have a look at what this looks like. So this particular case, it's a 4-class model. So we've got 4 classes, and it's although it's based on real sort of lab-based Raman spectra, it's artificial in the sense that I've then gone in and I've artificially put in some discriminating peaks, so you can just about see them here. So these are the mean spectra per class, and you can see, for instance, let's take class 1 in orange. You can see this peak here. So this orange pink peak here, this is the only peak which distinguishes class 1 from all the other peaks. Then for class 2, we have a peak here and also a peak here. And so those 2 peaks are the 2 discriminating peaks for class 2. And then so too for class 3, have 3 discriminating peaks here, here, and here. Class 0 has no distinguishing peaks. So what distinguishes class 0 is the absence of peaks. And that absence is an interesting little caveat that we'll look at later on. So the model itself is an extremely simple CNN in this particular case. So it should be fairly light to run, even if you've just got a CPU. Actually, it doesn't take too long to run. And it's pre-trained, so you've got your weights here that you can just download and run this. Of course, if you've got your own data, you'll be using your own model. Let's have a quick look. What is this cell doing? Okay, it's just giving us some performance metrics. Yes, an extremely good classifier. It's a bit of a contrived problem, right? This isn't necessarily a representative of what you would want to do in real life. But this is just to demonstrate how Spec-ReX works and that it can isolate those peaks, which we know are already there because it's already got the ground truth. So we'd expect it to be extremely overfit, basically. Okay, so this already I can see, not necessarily a mistake, but I can see GPT's made simplified something too much. So number of spectra to explain, that's just something unique to this live demo. Number of Rex iterations, now that is important. We'll come back to that parameter later on. The Rex mask value is also very important, but it's more than just linear or quadratic. And in fact, it's put in a little function here to check that it's linear or quadratic. There's more options than that. We'll run this cell anyway because, like I said, I looked before and it doesn't actually matter. This little check doesn't actually matter. So you know how GPT just does a lot of things which don't necessarily correlate to things later on. So it's just a little example here. What we've got here is GPT's created this function to create responsibility maps, and we'll look at exactly what a responsibility map is later. The important thing for now is what you really need is the model, the spectra, or a spectrum at least, and the device. That's all Spec-ReX really needs. These indices is just something GPT's decided to add extra on to keep a track of things, I'm sure. And you also got the mask value here. So like I was saying before, why is it put the mask value? Where did it put the mask value? So you got Rex mask value here, and you can put in linear here or quadratic here, but then it asks for the same information here. So you can see you can just override it here, and iterations, same with iterations there as well. We'll keep these. I would recommend keeping for now quadratic and just keep iterations at 20. We'll look later on exactly what difference that makes to the spectrum. And so this is actually going to calculate some spectra, so we'll see in real time how that works and how quick it is. So I believe there's 20 spectra being explained here. So every single spectrum is like a 5%. So you can see how long it takes to take one spectrum. So one spectrum, seconds, mere seconds. But you can see that if you do have hundreds of thousands or even millions of spectra, now it can take time. So just something for you to bear in mind as you go through your workflow. Okay, so that's now calculated. That's now created those responsibility maps, and we'll look at those in a second. So these are some plotting functions that GPT's come up with. It looks all sensible. So let's have a look at what it's come up with. Okay, that's just a function, so let's actually run it. Okay, excellent. So we'll begin with class 1 actually. So this is class 0, but we'll begin at class 1. So what you've got here, you've got the original spectrum, and in green you could just see the green peeking out here. That's the ground truth, so that's the known simulated feature. So that's this peak here, and then the sort of dark red bar here, that's Rex's explanation of that classification. So in this case, the ground truth is class 1. Indeed, the classifier did predict it as class 1, and then Rex will say, well, the reason this was classified as class 1 is because of this peak here. And there's a few other examples here from class 1 as well. Excellent, gets all of them pretty on the nose. Excellent. You can see there's a fair amount of noise in these spectra. So like I say, even though these are simulated spectra, I have added quite a lot of noise just to try to simulate some vague sense of realism. Then we look at class 2. So class 2, you can see, is defined by two features. So you've got one defining feature here and one defining feature. You can't quite see it here because the explanations is imposed on top of it. But there are two features here. And you can see that the model only uses one of these features to make this classification. So this is an important distinction here that I just want to make with regard to what you're explaining. So you're explaining what the model thinks is important, not necessarily what's going on in the real world. So in the real world, I constructed this particular class to have two defining features. However, just because of the way I trained it, it's, like I say, it's a little bit of a sort of a false environment. But because of the way I trained it, you didn't need both of these features. One of these features was enough to drive model performance. And that's quite typical, right? In modern machine learning, if you're using any sort of kind of deep learning in particular, the model will just learn the simplest shortcut. And in this case, you just need one of these features to define a class. And so that's a kind of use case for Spec-ReX. You can see, well, what is your model doing? My model is only using this one feature. Because I happen to know the ground truth, I know that it's missing another feature. And that's information about your model. Your model's not necessarily doing what you think it's doing, even though two features do distinguish between this particular class. Your model, well, this particular model, is only finding one of those features. And so too for the other examples in this particular class. And then if we look finally at class 3, which had 3 defining peaks, a bit more of an ambiguous use case. In this particular case, it's again just using one feature and largely ignoring the other two features. But you can see in this particular example, it is assigning some responsibility onto one of the other features whilst leaving the other one alone. So in this particular case, the model has learned sometimes to use one of the other features as well, or maybe a little bit of both of them, but that's far from universal. And in this particular case, it's very strongly needed to use this. So remember, these aren't identical spectra. These are different spectrum from the same class, to which I've added quite a lot of noise. So sometimes this model does want to use a second feature to make its classification. If we go back to class 0, now this is an interesting case and something you do need to keep an eye on in Spec-ReX. So if you remember, the previous classes all had very distinct Raman bands which were discriminated between the classes. But class 0 rather, is defined by the absence of features. So there is no single feature or no single set of features which drives this particular classification. So there's an absence of features which defines this particular class. Now when that happens, Spec-ReX will still run, and indeed any explainability method will still run. I think one of the advantage Spec-ReX has to some of the existing explainability methods, such as SHAP or LIME, will still return something which looks like it might be plausible. So it looks like you might have this sort of barcode feature and it might be picking out these certain peaks. However, actually the model's not using any of those features. We know it's not because they don't exist in the ground truth. So when that happens, what Spec-ReX will do is it will give this peculiar pattern where it picks up on the edges. It could be, in this particular case, happens to be the left-hand edge, but it could equally be the right-hand edge, or indeed both edges. You'll see those cases. So if you see this in your data, in your explanations, you know that something is going on with this particular class. There's something pathological has been going on with regard to your model given a particular class. Basically, the reason that the model's classifying in this class is in some sense distributed across the entire spectrum, and it's not a particularity of a single feature or set of features. So maybe a little bit of a limitation of Spec-ReX, but like I was saying before, it's a limitation of all post hoc explainability methods. I think in Rex it's just easier to recognize when that's the case. So something for you to keep an eye on. In my personal experience, when it comes to actual real life spectra, it's very rare for a class to be defined by the absence of features, or but defined by something which is distributed across a broad range of the entire spectrum. So I've yet to come across it in real life. Like I said, I use biomedical, mostly Raman spectroscopy. I've been looking at FTIR quite a lot recently as well, and I've yet to come across this use case in natively, let's say. But something I want you to be aware of, something for you to keep an eye on. So once we have that, I can't remember exactly what GPT's done next. Oh yes, so this is just one particular way of visualizing these responsibility maps. So you can see, the responsibility heavily localizes on this one feature. However, it's quite difficult to read off a graph of exactly how you do that, of exactly which band number it is. So another way of visualizing it, this is just a responsibility map for one of the classes. It was for one of the class 3 spectra. It wasn't this one, it may have been this one. I can't remember exactly. You can see that it's assigned a tiny little bit of responsibility to the second feature, so maybe it's this one. And then a lot of responsibility here. The reason it's useful sometimes to plot your responsibility map like this is it's just so much easier to localize exactly which spectral feature is being highlighted. You can see how very precise it is in this case as well. For those who are used to using SHAP or Lime or even GradCam, you'll see it much more diffuse. So Spec-ReX very precise in that regard. And the reason this will be easier is just because you can then, has it done it later on? You can look at, for instance, you can just take the argmax, and argmax will return the exact index of this, and you can find the exact wave number that's done. I'm pretty sure there's an example of that happening later on. So we've been looking at individual spectra, so we've explained individual spectra, but something else we could do, like I say, that's feasible in this particular case because I've just selected 20 spectra to look at. However, if you've got data sets of thousands, hundreds of thousands, maybe even millions, that's going to be intractable. So what can you do? Well, one thing you can start to do is look at the mean spectra and mean responsibility. So and that's what these plots here are, both the mean spectrum by class and the mean responsibility. So I've taken the responsibility map separately, taken the mean of those, taken the class mean separately, and taken the mean of those. And you can see that you basically get a summary of the results that we looked at before, where it's localizing to a particular feature, and in this case, in the case of the 3 classes, it's demonstrating shortcut learning basically. So you can start to make decisions about your model. Are you happy with your model only having learned one feature of these 2 features, for instance? If not, you might want to try to retrain. So in this particular, like I say, this particular contrived example with this particular data set, I could force the model to learn both of these features. So both of these features have to be present for this to be deemed class 2. So I could go back and retrain the model with that in mind if I wanted to. Oh yeah, so here's an example of it actually taking the argmax, the nan argmax in this particular case, in order to find those selected labels not defined. What has gone on there? Let's have a quick look. That's because I've not run this cell. Like I said, I've run this cell, I ran this example before just to make sure everything was what I thought it was. and it will then return those peaks that I picked out before. Less well defined when you've got something a bit broad here, but you could do something like I think SciPy have quite a good function if you've got multiple peaks, which will happen a little bit more with real data sets. SciPy's got a good sort of peak finder function which can help with that. So I just wanted to talk you through this animation to give you a better idea of how Spec-ReX works, and with that intuition it'll help you just make some decisions about which parameters you might want to tweak or not. So just to talk you briefly through this before we hit go. So in the background obviously we have this Raman spectrum. So this is the spectrum that we're going to be explaining. You can see the vertical bars here. These are the ground truth signal. So this is where we'd expect the responsibility to accrue. Although, as we said, we already saw that this model doesn't look at both of these features. It only picks one of those features. And we'll come back to exactly what this blue line is in a moment. On the right hand side though, you have the same two ground truth features. The red line here though, so this is going to be the responsibility map, and you'll see that sort of build up with time. However, I just want to look first at just maybe one mutant. So in the theory of REX, a mutant refers to a spectrum which has been perturbed or occluded in some sense. So what Spec-ReX does is it'll chop the spectrum up into sections. It's actually, even though you can't see it, it's actually chopped up into 4 sections, but it looks, in this particular instance, like it's just chopped up into 2. And what it's done is it's kept one half of the spectrum, and it's erased in some sense the other half of the spectrum. Now what do I mean by erased? We've replaced all the values with what we might want to call neutral values. This is what quadratic refers to in this particular case, so you can see exactly where it's started to occlude the spectrum, and then just replaced those values with a quadratic. If you look extremely closely, and we'll look at this in more detail in a moment, if you look extremely closely, you'll see there's a tiny little bit of noise that's been added to this. So that's just both a quadratic function and the use of a little bit of noise is just to make the occluded part of the spectrum as realistic as possible. And this is something unique that Spec-ReX does, which no other explainability method that I know of anyway does. But we'll look at what difference that makes by looking at some other values that you might want to use a little bit later on. For now, the pertinent point is what happens is we then take this blue spectrum, so that's all of this original half of the spectrum, and with this occluded part of the spectrum, so all of this goes into the model, and you simply ask or look at the output of the model, and does it retain the same class? In this particular case, because it's green, it has preserved the class. So we put this blue spectrum in, and the model still thinks that this is a class 2 spectrum. It correctly thinks that this is a class 2 spectrum. So what we do is we take the non-occluded part, or the area of the non-occluded part, so it's up to about wave number 1000, and we add that to our responsibilities, because you see now this bump here appears in this responsibility map. So now let's just play this animation. Let's just see how REX will go through the spectrum, performing lots of different occlusions, and these are just random partitions that it makes, inputs a neutral value, in this case a quadratic, and then asks the model, is this the same class? Is this spectrum still the same class? And you can see every now and then the red text appears that the target class is lost, and what that means is whatever the spectrum it randomly generated lost the information, lost the discriminating information. And so when that happens, we don't look into those regions anymore. And so as the animation goes, hopefully you'll see that the algorithm focuses in, sort of hones in more and more on the discriminating peak. So hopefully that's given you some intuition as to how sort of Rex is working in the background. But now let's look at how some of the parameters that you can play with sort of make a difference to this. And just before we scroll up to look at those parameters, just bear in mind what this looks like. So this is the quadratic occlusion strategy. And you can see how the peak, it sort of builds up, peaks at 25 in here. This accumulated responsibility, by the way, we normally normalize it on the output. It's arbitrary units basically, so don't have to worry about the actual number itself. We normalize it anyway. This animation actually was also created by GPT. It's very helpful for those sorts of things, but my word, it is verbose. So let's scroll up to the top and see what's going on. So maybe the first parameter we could play with, since we're on quadratic, is to add some more noise. Like I said before, it did accrue, we did add a little bit of noise to this spectrum, just in order to make it a bit more realistic. However, it's a very sensitive parameter. If you've got normalized spectra, I would say just stick to the default, which is 0.01. But if you've got noisier spectra, you want to be more stringent with your data on your model, really, then you can add some more noise. You can hopefully just intuitively see straight away how much more noise is being added. And you can see what difference it makes. It makes a huge amount of difference. And in fact, in this particular case, the noise is overwhelming the signal. And that kind of makes sense, hopefully, because if we freeze one of the frames here, you can see how much, the noise is basically the size of the signal here, and so the noise overwhelms the signal. So that's why you do need to be careful with this parameter. I've set it to a very low value for now, and in fact you can just turn it to 0. However, it does make a difference. Let's set that to 0 now and see what happens to the animation. So now it's just a pure quadratic. In the first instance, when I started playing with this, I didn't think it would make that much difference. And in terms of the overall picture, it doesn't make a huge amount. As you go through more and more iterations, you can sort of see it does pick out the same peak, but it does so less efficiently, basically. So I would recommend having a tiny little bit of noise here. The default of 0.01 should work if you've got normalized spectra. These particular spectra were normalized to have a mean of 0 and a standard deviation of 1, so SNV normalization. But any other sort of normalization, I think this value should work fine. The other variable you may want to play with, just if for nothing else, your own interest, is the actual occlusion strategy. So let's put mean in here. So mean is a common default for a lot of other explainability methods. So probably, not necessarily, but probably if you're using SHAP, it will default to 0. And you can see how in this particular case, the mean, because of how the spectra were normalized, the mean coincides with 0 here. And hopefully it's intuitive to those people who are used to working with spectra. If I just freeze one of these, how unrealistic looking these sort of simulated spectra are compared to the quadratic variant. However, even in this case, it does localize eventually to the same ground truth area, but in a much slower and with quite a lot more noise as well. And finally, why not look at linear, because that's another option that you have. So let's put in linear here. Random, I wouldn't even worry about that one actually. Let's just run linear. Let's see what difference that makes. So linear doesn't have any noise added to it. It's just taking a straight line from wherever it's occluded down to one of the anchor points. The anchor points on the edges, by the way, are the ends of the spectrum. And again, you can see it does localize to the ground truth signal, so it still does work, but again, just not as efficiently. So the last thing I wanted to draw your attention to was the number of iterations that Spec-ReX uses and how that interacts with the building of the responsibility map. So the first thing that you might notice is that actually one single iteration generates many mutants, and each mutant builds up more of the responsibility map, and that starts to accrue. However, within that one single iteration, it's kind of a bit of a guided search, and so as you can see, it will hone in more and more on the most responsible features and stop exploring the rest of the space. So just to make sure we don't get stuck in a local minima, so to speak, we'll then do a second and more iterations, and each iteration just uses a different random seed, and it just allows us to make sure that we explore the entire space of sort of possible partitionings and inclusions. The subsequent iterations, they build on the previous iteration's responsibility map. So as you can see here, we're now in iteration 3. You can see how the responsibility map is just becoming more and more peaked. So in terms of how many iterations are you going to want to run for your dataset, well, a few things you want to take into account. So for this particular dataset, like I said, it's a very simple dataset, maybe a little bit contrived, not particularly realistic, and it was incredibly simple. The task was incredibly simple. And so actually even just one iteration was enough to find the pertinent features in that particular case. However, what I found in more realistic datasets, biomedical datasets, the default of 20 is quite a good number. So if in doubt, just leave it at 20. I have with some datasets which have incredibly subtle spectral features, I have dialed it up as high as 60. And I did find that particularly helpful. That does though come with a cost of time. It just takes a fair bit longer to run. So that's your trade-off you're trying to make. Increased accuracy costs you more time. What I'd recommend that you do perhaps is just take a subset of your data, maybe just a few hundred spectra or so, and experiment with the number of iterations. Maybe just try with a default value of 20 and see if it's picking out spectral features that you might anticipate. If it's not, if there's more subtle things going on, you might want to increase the number of iterations. Or if with 20 iterations it's really doing really well and picking out the spectral features very quickly, you might in fact want to reduce the number of iterations. And then once you're happy on that subset of data, then go to your entire data set and get the responsibility maps for your entire data set. So that should be enough information for you to get started on your Spec-ReX journey. I'll leave you just with a couple of websites that may be of interest to you. The top one is my blog post, but I put lots of information up there if you're interested in this kind of subject, both in terms of vibrational spectroscopy and explainable AI, and in particular the intersection of those two. The second link there to GitHub, so that's the general Rex repository. So Rex is a part of a much larger body of work in which we look also not just at vibrational spectroscopy, but we look at other 1D data inputs such as ECG and audio data. Also look at 3D information, for instance, MRI scans or CT scans in 3D space. So this framework is much broader than just spectral data. So if you're interested in other data types, you can have a look there. Spec-ReX is also there, But we're constantly updating things, so do feel free, leave any feedback. If you come across any bugs, please do let us know. We will look into them and correct them. We're always looking to improve and refine this, so any feedback more than welcome, and GitHub is probably the best place for you to do that. Although feel free to leave comments here as well. So like I said, we are updating it, but on my own GitHub account, what I'll do is I'll leave a sort of preserved version of Spec-ReX that we went through in this tutorial, so that this tutorial will always work, at least with that branch. And finally, also like to acknowledge Chai. So Chai, a sort of a group of various universities or groups within universities throughout the UK, interested in sort of using causality for healthcare related AI. So that's what Chai stands for. And they're, as the name suggests, interested in applying causal reasoning and causal thinking into the healthcare domain, especially in light of recent AI advances. So indeed, the work that we're looking at Spec-ReX and Rex more generally is based on a theory of causality called actual causality. So if you're interested in that side of things and how you might want to use causal thinking in your work, then check out their website there. So with that, I'll leave you to play around with Spec-ReX, get to know it, and like I say, any feedback more than welcome, and I'll see you next time.